Hello, my name is Eli Kennigstein, and today I'm happy to share some of my work on instrumentation development for X-ray Transient Absorption Spectroscopy, and in particular I'd like to share what we've done with the X-ray Multiprobe data acquisition technique. This is a technique that we use at the Advanced Photon Source at Argonne National Laboratory. The focus of our instrumentation development is around understanding photochemical reactions, and in particular, the photocatalytic generation of fuels like molecular hydrogen from reactants like water. The absorption of a photon kicks off a chemical reaction, and the mechanism is defined by the sequence of molecular structures which brings the reactants and turns them into products. Now, each distinct intermediate species produces a fingerprint in the X-ray absorption spectrum, and this fingerprint contains information about the molecular structure of that species. Here's an example of the sample environment that we use to study photochemistry with XTA, and the idea is that we have a fast laser pulse that hits the sample and initiates a photochemical reaction. The reaction that occurs in the sample changes the X-ray absorption spectrum, and those changes are measured with these avalanche photodiodes here. And of course, these changes reflect the structure and the kinetics of the intermediate species. Now here I've only shown one synchronized X-ray probe pulse, but in reality, there are many more X-ray pulses than there are laser pulses, and the idea of X-ray multiprobe data acquisition is that each one of these pulses generates a spectrum, and we can measure up to 20,000 time-resolved spectra simultaneously. For example, this diagram shows how the spectra at 3 different time delays are acquired from these 3 bunches after the laser, and the temporal spacing of each spectra is given by the X-ray pulse spacing, and in APS 324 bunch mode, that's 11.37 nanoseconds. This figure contains osmium L-edge XTA data obtained by exciting an osmium photosensitizer molecule and acquiring the data with the X-ray multiprobe technique. Each point on this data surface represents the change in absorption at a particular energy at a given time delay from the laser. And the instrumentation for X-ray multiprobe is described in detail in my forthcoming publication. So just to summarize here, the X-ray multiprobe data acquisition technique, also called XMP-DAQ, measures the XTA spectrum at a huge number of pump probe time delays simultaneously. And this allows you to efficiently map out a photochemical reaction using XTA. And the spectra obtained are separated by the X-ray pulse spacing. Here's some data that we acquired by exciting ferrocyanide at 255 nanometers. And this data illustrates the limitations of the XMP technique. And in particular, you can see there's a big difference in the spectra observed between the first 2 bunches. And the reason for that is that there's a really fast chemical reaction that's going on in the first 10 or so nanoseconds that we can't resolve with the 11 nanosecond bunch spacing. This motivated us to develop a technique that has the advantages of X-ray multiprobe DAQ, but can also map out fast photochemical processes. And this new technique we call XMP with asynchronous acquisition. Generating an asynchronous acquisition boils down to cleverly picking the laser repetition rate. The laser repetition rate is defined in terms of the X-ray repetition rate and this number n here. And for an asynchronous acquisition, n should be a rational number, but definitely not an integer. For example, here I have a diagram representing n equals 7.5. Now here, these blue lines are representing the X-ray pulses, and the red lines are representing laser pulses. And the fact that the laser repetition rate is not an integer submultiple of the X-ray repetition rate, it means that the time delays at different laser pulses are different. So for example, the time delays of these X-ray bunches following this laser pulse are different than the time delays of the X-ray bunches following this laser pulse. But the important point here is that in the X-ray multiprobe technique, we acquire a spectra with every single one of these X-ray bunches. And so the fact that the time delays of these X-ray bunches are different than the time delays of these X-ray bunches, it's inconsequential because we actually measure all of them simultaneously. And so using this technique, we were able to simultaneously acquire XTA spectrum every 1.42 nanoseconds after a laser pulse. And here's the data that we generated here. This was on ferrocyanide at the iron K edge. And we were exciting ferrocyanide at 255 nanometers. And you can see that we really nicely resolved those early time spectral changes. So you can see, comparing the data acquired with the old X-ray multiprobe technique with the data acquired with the new X-ray multiprobe technique using asynchronous acquisition, we can see that the asynchronous acquisition technique can really nicely resolve these early time changes in the X-ray absorption spectrum, whereas those same changes are pretty much entirely missed with the old XMP technique. And so now I want to talk about how we are analyzing this data. And the idea is that we really want to generate a global fit of the data. And the global fit contains the identity of the intermediate species in the reaction mechanism, as well as the kinetic coefficients that describe the interconversion between the species. But what we have is the raw data. And of course, the first step is to take the singular value decomposition, and that produces this reduced dimensionality data set. We can't go directly from the reduced dimension data set to the global fit because that requires n² free parameters, where n is the number of species participating in the reaction. So in order to extract quantitative information from our raw XTA data, what we really need to do is introduce these mechanistic constraints. And when we do that, we actually can achieve a pretty unique global fit. And these mechanistic constraints come in two flavors. Now, the first are spectral constraints, and you can either measure experimental spectra or you can calculate the spectra. Now, the other kind of constraints are kinetic constraints, and these take the form of the kinetic equations that describe how the concentrations of the various species evolve in time, and these kinetic equations reflect the structure of the reaction mechanism. So in our case, we took our raw XTA data, we took reference spectra, and we took a kinetic model. And these three things together enabled us to generate a unique solution, and we could also even extract these kinetic coefficients. The first way to assess the quality of the global fit is to compare the spectra that are generated in the fit with the reference spectra. And what you can see is that the agreement is actually really good in this case. So that's pretty gratifying to see. So the second way to assess the quality of the fit is by evaluating if the kinetics that are generated by the fit are compatible with the reaction mechanism that you're assuming. And what you can see here is that these kinetics are describing the bimolecular recombination of this photooxidized species here with these hydrated electrons. And so you can see that our kinetics are indeed compatible with the expected mechanism. And that's pretty cool. And so just to summarize, X-ray multiprobe data acquisition simultaneously measures the XTA spectrum at a set of time delays. And this allows us to experimentally test a photochemical reaction mechanism. And we can extract the kinetic coefficients. This new development of asynchronous acquisition with X-ray multiprobe, it pushes these capabilities to the nanosecond timescale. In the future, we'd like an unbiased way to generate mechanistic proposals to test against the data. And this idea is inspired by computational catalysis algorithms, which propose reaction mechanisms using a low level of density functional theory. The only difference from that approach is that we wish to calculate an X-ray absorption spectrum from each structure in the proposed mechanism and compare it with the X-ray transient absorption data. And we think that this combination of simulation and data will be a powerful technique to study photocatalysis in the future. The second direction for future development is to decrease the spectral time spacing from 1.42 nanoseconds to about 10 picoseconds. And we think there'll be a lot of fun samples to measure with this fully asynchronous technique. And with that, I'd like to conclude by thanking everybody that worked hard on this project, in particular, Xiao Yi, my postdoc advisor, Anne-Marie, Don, and Gilles were a big help on this project, and we couldn't have done anything without Guy, and Chris helped out a lot at the Beamline. So I'd like to thank all these people a lot. Also, this project was funded by LDRD. And I'd like to thank all of you for your attention. Please feel free to reach out to me at my email address, and have a great day. Thank you very much.